All right, so let's finish off our discussion of electronic structure and talk about our last quantum number. We already talked about our first three, N, L, and ML, which can describe an electron in terms of its size, its shape, or its orientation. And that describes what type of orbital that electron is in. These electrons are, around the nucleus of an atom, and we're trying to describe the behaviors of these electrons. So our last quantum number is ms, or electron spin. So we have to have this fourth quantum number because of Pauli's exclusion principle. So all the orbitals that we've talked about. So orbitals, when I say orbitals, I mean our different ml values that we can have. So a maximum of 2 electrons can reside in each of those orbitals, each one of those ml values. The problem comes into having Pauli's exclusion principle, which says that no 2 electrons in an atom can have the same 4 quantum numbers, N, L, ML, and MS that we're talking about now. But we already talked about the first 3. So by introducing spin quantum number, we can put 2 electrons in one orbital. So I can give an example. Let's say we have an s orbital, right? So this would be an L equals 0. The only possible ML value for an s orbital is 0. So there's just one orbital within an s subshell. So I already said that we can put 2 electrons in each of these orbitals. So in order to do that, in order to put 2 electrons in those orbitals, those 2 electrons will share the same N, L, and ML values. Let's just say this is N equals 1. All right, so if we put 2 electrons in this box, they will share the same 3 quantum numbers. So where ms comes into play is we can have a spin up electron and a spin down electron. So they will have different ms values. So those different quantum numbers that correspond to ms, or our magnetic spin quantum number, is a positive 1/2 spin or a negative 1/2 spin. So you can just think, positive is up spin, and then we have our negative 1/2 is a down spin. And so those are the only possible ms values that you can have. Those are the only 2 spins possible for an electron, or is either positive 1/2 or negative 1/2. All right, and so if you look at these 2 electrons that I placed within this 1s orbital, there are 2 electrons, and that's the maximum number of electrons that we can have. So one of these electrons has a ms equal to positive 1/2, and then the other one has an ms of negative 1/2. So those 2 electrons will share the same 3 quantum numbers, but that last quantum number, ms, they are different. So one's positive 1/2, the other's negative 1/2. So then we obey Pauli's exclusion principle. So really the big takeaway from this slide is that every orbital can hold a maximum of 2 electrons. So if you draw each ML orbital box, you can fit a maximum of 2 electrons in there. And that will bring us to coming up with electron configurations for different atoms. So just keep that in mind, that you can put 2 electrons in each orbital, each one of those boxes. All right, so we already talked about this, that for a set of quantum numbers like n equals 1, L equals 0, ML equals 0, describes a 1s orbital. So you can, draw a box to represent that orbital, but it's spherical. If this is a 1s orbital, you can put 2 electrons, one up and one down. So each of them have different ms values. And so with Pauli's exclusion principle, since we limit 2 electrons per orbital, we can calculate how many electrons we can have within a subshell. So if we look at these different L values, these subshells, if L equals 0, yeah, that's an s orbital. Then L equals 1 is a p orbital, and so forth. So you can think of the number of orbitals we can put into there. These are our number of ML values for each one. So for an s orbital, there's only an ML of 0. For a p orbital, there's an ML of negative 1, 0, positive 1. For a d subshell, there's a total of 5. So that's negative 2, negative 1, 0, positive 1, positive 2. And then F, there's a total of 7. So I'm not going to draw all the boxes. But so each one of these boxes represents an orbital within each of these subshell types, or these different shapes. Each of those boxes can hold a maximum of 2 electrons. So because of our ms quantum number, right, we can have a positive 1/2 or -1/2. If each one of these boxes can hold 2 electrons, then that means an s orbital can hold a maximum of 2 electrons in that one box. A p subshell, because it has 3 orbitals, can hold a total of 6 electrons because we can put 2 electrons in each one of these boxes. And then for a d subshell, since there's 5 orbitals, we can hold 10, and then for f, we can hold 14. So keep that in mind when we are doing electron configurations for arrangements of electrons for the different elements. And the great thing about these different maximum numbers of electrons, is that you don't really need to memorize them. I mean, I think with time you'll come to know it, but the periodic table actually tells you the maximum number of electrons based upon its shape. Let me go get my periodic table. Okay, so here's my periodic table. So we see the different parts of our periodic table. And we can kind of break the periodic table into subshell types. So in our 1A and 2A groups, this is called our S block. All right, so each of these elements in these two columns, in these two groups, the valence shell electrons, which we'll talk about, are s electrons. So you can see one, like lithium and beryllium, that's like 1 electron in the s subshell, and then a second electron in the s subshell. So there's a maximum of 2 electrons that can be within the s subshell. Over here on the nonmetal side, this is what we call our p block. So if you count, how wide the p block is, it's 1, 2, 3, 4, 5, 6 elements wide. So if you look at our table, 6 is the maximum number of electrons within our s subshell. And then finally, if you look at the transition metals, this is our D block. So our D block, you can just predict how many elements wide this is. It is exactly 10 elements wide, each element representing one of the electrons that we can place within our D subshell, filling it up with up and down spinning electrons. So we're going to move away from the Bohr model of the hydrogen atom and start talking about elements and how electrons are arranged within all of our different elements on the periodic table. So have your periodic table handy, because we'll need that, because we're going to be talking about electron configurations and how electrons arrange themselves within atoms, multi-electron atoms, essentially meaning everything other than hydrogen. So we're moving away from the Bohr model of the hydrogen atom, and we're talking about elements now. So there's 2 different ways we can talk about arranging electrons within an atom. The first one is using what we call the electron configuration. So we have to keep in mind our N values, our L value, letter designations, and how many electrons are in each of those subshells. So this basically is the template for writing out a subshell, the electrons within one subshell. So typically you write the n quantum number, your principal quantum number, out front. So n, this is our principal quantum number, and it tells us the shell that that electron is in. So n will be a number, so an integer value. L, this tells us what subshell that electron is in. So these are our letter designations, such as S, P, D, etc. And finally, in the subscript next to the subshell letter designation are the number of electrons in that subshell. All right. So with practice, you'll get how to write out electron configurations. So let's just do an example here of how to write the electron configuration for a hydrogen atom. All right, so I see hydrogen is right here on the periodic table. So you want to ask yourself, how many electrons are in that element? If I ask you, okay, what's the electron configuration for boron? Ask yourself, how many electrons are in that element? All right, so if we look at hydrogen, because of its placement on the periodic table, if we have a neutral hydrogen atom, there's 1 proton, so that means there also has to be 1 electron. So we just need to place 1 electron. And so hydrogen is in our S block, and we start at the beginning. So we write essentially the location of that electron is in a n equals 1 shell. It's in a L equals 0 subshell, or an S subshell, and then there's only 1 electron in that shell, because we only have to place one electron. Because it's a hydrogen atom, there's only one electron. Right? So hydrogen is the simplest example because we only have to place one electron. But if we look at boron, boron is here on the periodic table. So we have to locate and place all of the electrons, 1, 2, 3, 4, 5 electrons in order to get to boron. Boron has 5 electrons that we have to place. So let's do that. So typically how I approach electron configurations is I start at the very beginning. So I start at hydrogen and I just start filling all of my orbitals until I get to my desired element. So in this case, it's boron. So if we remember, we always start with our 1s orbital, and that orbital can only, or sorry, that subshell, so 1s subshell can only hold 2 electrons. So that brings us to hydrogen, helium. So an s orbital can only hold 2 electrons. But we need to get to 5. So next, after helium, we go to lithium. So lithium is also in the s subshell. All right. So we have to now fill our next subshell, which is our 2s subshell. And it's an s orbital, so again, it can only hold 2 electrons. So we'll place 2 electrons in there as well. All right, so that brings us to lithium, beryllium. And now the 5th electron that represents boron is within a p subshell. So this is a 2p subshell, and there's only 1 electron in it because it's boron. If this question was asking for like nitrogen or something, then we would put 3 electrons in the 2p subshell. But in this case, since it's boron, we only need to place 1. So this is the electron configuration, the full electron configuration for boron: 1s2, 2s2, 2p1. And so you can use the periodic table to help you here, to figure out, are you filling an s or a p orbital? And then you just kind of have to know how many electrons go in each of those subshells. All right, so electron configurations is the first way we can represent electrons in multi-electron atoms. So I have a bit of extra credit here for you. All right, so this is for chapter 6. It's worth 2 points. So if you email me the answers to this, I'll give you 2 points on midterm 3. So I'll just describe what I want you to submit. So I want you to submit for a magnesium, a neutral magnesium atom, and an oxygen atom, these different things. So the first thing I want you to send me is the full electron configuration for magnesium and oxygen. So we already did electron configurations for hydrogen and boron. Right, so you should be able to do this first one. In the next coming slides, we will look into doing orbital diagrams, noble gas shorthand, the number of valence electrons, and what paramagnetic and diamagnetic mean. So I just want you to have this on the back of your mind as we move forward with these different topics. So we have this first one in mind: full electron configuration of atoms. We just use the periodic table and we count and start filling our different subshells until we get to our desired atom or element. So the next part are orbital diagrams. This is another way we can show how electrons occupy themselves in orbitals. So I kind of already showed you pictures of this before, but we can represent an orbital as a box. And then each of the electrons can be represented by an arrow, either spin up. So this is our ms of, positive 1/2, or a downward pointing arrow. This would be our negative 1/2 spin. All right, so we can represent these electron configuration using just like a pictorial diagram instead. They mean the same thing. It's just, in this case, an orbital diagram, you can see more clearly how electrons are arranging themselves within these orbitals. So if we remember our electron configuration for hydrogen, it was just 1s1. We just placed 1 electron in it, right? For boron, there are 5 electrons we had to place. So essentially, each box represents a subshell or orbital. So in this case, a 1s subshell only has 1 ml value. So there's only 1 orbital. We only have to place 1 electron. So we just have 1 spin up electron. You could have put a spin down electron. It doesn't matter. All right. So then if we look at boron, so instead of writing out 1s2, 2s2, 2p1, we can draw these as boxes instead, keeping in mind how many orbitals are in each subshell. So within our 1s and 2s subshells, there are only 1 orbitals per those subshells, because an L of 0 only can have an ML of 0. This is ML of 0, L of 0, And so you see here, because the superscript is 2, that means there's 2 electrons in each one of those orbitals. So you see our spin up and spin down electron there. And then the same thing in our 2s orbital. So those 2 orbitals are completely filled, or subshells are completely filled. Where it gets a little bit weird is our 2p subshell. So within a p subshell, so that's an L equals 1, within an L equals 1, ML can equal -1, 0, or -1. So that's what each of these boxes represents. So the first box here is like an ML equals -1, next it's ML equals 0, and then +1. And so now we can place our electron, our 1 electron that's within our 2p subshell, into that first box there. And so in this case, we just arbitrarily put a spin up electron. All right, and so here are the orbital diagrams. So that's how you write that. You take it exactly from how you write out the electron configuration. You just draw it instead of or you actually draw out the orbitals as each box. And so you see here, at least in our boron example, we have 2 types of filling of orbitals. In our 1s and 2s orbitals, we see that there are paired electrons, that there's a spin up and a spin down. They're paired in both of these different orbitals. In our 2p subshell, we just have a lonely electron there, just spinning up all by itself. So this has some meaning to it. So when 2 electrons are in the same orbital, so the same box, and they're both spinning in opposite directions as you should place them, their spins cancel, and we call that paired. We call those electrons paired, that they have a partner. They have a spin up and a spin down. And so when we have a single electron in an orbital, such as our 2p subshell, we call this an unpaired electron. So if a substance or an element, as you write out its electron configuration and orbital diagram, if a substance contains an unpaired electron, then we call that substance paramagnetic. And the reasoning is because of the magnetic quantum number, or the magnetic spin quantum number, that unpaired electron, because its ms equals, a positive 1/2, that electron is affected by a magnetic field. So we call it paramagnetic. If we have a substance where all of the electrons are paired with one another, then the substance is diamagnetic and it's not affected by a magnetic field. So an example here, so hydrogen. So hydrogen with just 1 electron, this is our 1s orbital, this would be paramagnetic because there is just 1 spin up electron, it's unpaired. So that, how I've drawn it, there is an unpaired electron. So an example of a diamagnetic substance is if we just go 1 element over, helium, which has 2 electrons, still within the 1s subshell. So we get a spin up electron and a spin down electron. So these 2 electrons are paired. So this would be a diamagnetic substance. So if we had a helium sample, it would be unaffected by a magnetic field. While if we had just 1 lonely hydrogen atom, which doesn't typically exist in our universe, then it would be affected by a magnetic field because it has that unpaired electron. So within our hydrogen and boron example here, both of these substances, according to their orbital diagrams, are paramagnetic because they both have unpaired electrons. All right, so let's move on to Hund's rule and talk about how do we fill electrons properly within p and d subshells. In both of those subshells, we have multiple orbitals. So that's what I mean by degenerate orbitals. A p subshell has 3 orbitals and a d subshell has 5 orbitals. So what Hund's rule says is how you need to place electrons within those p and d subshells is you want to maximize the spin of the electrons first, and that will help you achieve the lowest energy of the atom when you're writing it out. So essentially what you need to get out of Hund's rule is that when you fill orbitals in a p subshell or d subshell, you want to fill those electrons singly before you start pairing them up. You can kind of think of an analogy like seats on a bus, that typically people will want to be in like completely empty seats first as people start filing on until all of the seats are filled, and then you have to start pairing up folks to people in like a bench seat. So kind of think of it like that. People behave kind of like electrons in this case. So let's look at an example, carbon. And what do I mean by how do we fill up these subshells singly before we pair up? So if we look at carbon, carbon only has one more electron than boron. Right, so right here. So it has the same electron configuration, except at the very end, it's 2p, 2 electrons within our p subshell. So we need to place 2 electrons in our p subshell. So how are we going to do it? So in this first example, we pair up the electrons in that first orbital. So we don't want to do that. We don't want to do that. That will not maximize energy. If we actually look at the definition of Hund's rule, it says we want to maximize our spin. So if we actually look at the spin of these electrons, one of them is spin up, so that's a positive 1/2, and the other one is a negative 1/2. So overall together, those two paired electrons has an overall spin of 0 because they add up. So let's look at the next example. Well, okay, if we place one electron spin up and then the next electron, I feel like putting it spin down. Well, so they're not paired, but they have different spins. So they're in different orbitals, but they have opposite spins. So one has a positive 1/2, the other one is negative 1/2. So again, that has a total spin of 0. We want to maximize the spin, not minimize it. So this is also not how we pair up our electrons in orbital diagrams. So the last example here is the correct way that we write out the orbital diagram for carbon. So instead, in that p subshell, to place those 2 electrons, we want to place them each in their own orbital, both spinning the same direction. So if they're both spinning the same direction, let's just say that's like positive 1/2, positive 1/2. So if you add that up together, you see that the total spin is equal to 1. And so that's what Hund's rule says by maximizing the total spin of the electrons. And that is our lowest energy way to write out the electron configuration. So this is the correct way to write out electron configurations when you have to place more than one electron in degenerate orbitals. And so if we look at the ground state of a carbon atom, you see, because we have 2 unpaired electrons, that this atom, carbon, is paramagnetic because it has 2 unpaired electrons. So if you're doing questions as above and you write out the orbital diagram incorrectly in the filling of the electrons incorrectly, you might get an incorrect paramagnetic diamagnetic solution there. So remember, we want to place electrons singly before we start pairing them up. So let me just show you another quick example of pairing up electrons. Let's say we want to write out the electron configuration and orbital diagram for fluorine. So fluorine has 9 electrons. All right, so its electron configuration is 1s2, 2s2, and if you look on the periodic table, it's the 5th element along the p block, so it is 2p5. So to fill up the electrons in that p block, so again, I'm going to draw out my orbitals within my 2p subshell. So I need to place 5 electrons within that group. I'm only doing the last one, so let's just kind of forget about the s orbital for now. We're just going to look at the p orbital. All of these orbitals are of the same energy, so the best way to maximize the stability of this fluorine atom is to place all 5 of those electrons singly at first. So I'm going to put 1 electron, 2 electron, there's my 3rd electron. Now there's nowhere else I can put them. So we filled it all up. And I still need to add 2 more electrons. So those last 2 electrons will be spin down like that. And this is how we maximize the spin of 5 electrons within a p orbital. So you see how I fill it singly first, and then I start pairing them. All right, so we're about to practice doing more electron configurations. But I just want to introduce Aufbau's principle, which basically says that when you fill up your electron configurations, that you start at the bottom first, the lowest energy electrons first, which will be the electrons closest to the nucleus. So kind of our strategy for doing electron configurations, like if we wanted to do something like aluminum, if we wanted the electron configuration with aluminum, you start at hydrogen first and just start filling everything up until you get to aluminum. That's essentially what Aufbau's principle says, is that just place the electrons one by one until you get to the element that you want. And that makes us think about the ordering of the orbitals in terms of their energy. So if you start at hydrogen, make your way to aluminum, then you obey Aufbau's principle. Um, and so the energy of the orbitals, because we're talking about that, how that changes as you go across and down the periodic table, as your n and l and other quantum numbers change. So essentially here, energies of orbitals depend on your n and l values. So energy increases as n increases. So that's why we always start with our lowest energy electrons first, which would be our hydrogen, starting at hydrogen because that's an n equals 1. So we start at the bottom, build our way up. So yeah, energy of your electrons increase as n increases. Within a given shell of n, your subshells increase with increasing L. Sorry, your energy of your subshells increase with increasing L. So essentially what this means is that your S subshell is the lowest energy, then it's your P subshell within an N shell, and then your D, and then your F. All right, so for example, a, a, a 2s orbital is lower energy than a 2p orbital, or a 3p orbital is less energy than a 3d orbital. And what that means when filling up electrons is that you will fill up your 2s before you fill up your 2p, or you will fill up your 3p before filling up your 3d. All right, and then finally, the last bit about energy here. So all the orbitals within the same n and l, so that means your different ML values, your different orbitals, they all have the same energy. So essentially, all orbitals within the same N and L are degenerate. So I mentioned this word before, degenerate. And what degenerate means, degenerate, it just means has the same energy. So for example, if we were talking about a 3p subshell, so that's an n equals 3, L equals 1, that orbital, or sorry, that subshell looks like this. And we kind of already draw it this way. All of these ML orbitals have the same energy. And that's why we fill up those electrons singly, because they all have the same energy. All right, and then there's some exceptions that we'll talk about later, that there are some crossover for some elements that we don't follow these rules exactly the same, but just keep those exceptions in mind. But for the majority of the elements, if you fill them up this way, then you got it. But really, we don't even actually have to memorize these rules. As long as you understand that this is the S block, this is the P block, and this is the D block, there's not really much you have to memorize, except that boron starts at 2p, hydrogen starts at 1s, and scantium here starts at 3d, and you just kind of fill up the electrons until you get to where you want. All right, and so with all of these rules in mind, that leads to, this is the ordering of all of the different subshells. So you'll fill up 1s, 2p, or sorry, 1s, 2s, 2p, 3s. So again, I never really memorize this ordering, as long as I know that hydrogen starts at 1s, boron starts at 2p, scantium starts at 3d, then as long as you understand filling electrons one by one, then you'll get to where you need to go. All right. All right, so now let's do some examples. So let's do an electron configuration, or look a little closer at the electron configuration for chlorine. So chlorine has 17, a neutral chlorine atom has 17 electrons. So this would be the electron configuration for chlorine. Again, using the periodic table, you don't need to really memorize the ordering of this if you just know that our desired, or where we want to stop is chlorine. Just start at hydrogen and know that this is a 1s, fill up 2 electrons. Then you go to lithium, so 1s2 there, and then lithium is 2s2. Then you go to boron, so there's no such thing as a 1p. So when you get to boron, remember that starts at 2p. So boron to neon, that's 2p6. There's 6 elements, so 6 electrons there. So next after neon, sodium. So sodium, I always remember this is 1s, 2s. Sodium would be 3s. I'm going to fill it up the whole way, so 3s2. And then aluminum, since boron is 2p, aluminum is 3p. So aluminum to chlorine, that's 5 elements, so 5 electrons. So this would be 3p5. So that's how we got that there. So I don't memorize the ordering. I just kind of look at the periodic table. All right, and so we can write out the electron, the orbital diagram for this too. So each one of these subshells gets its own orbital diagram, where the S's only have one orbital, the P's have three. Because of the different MSs, and so you see the ordering there. And so the only subshell that has unpaired electrons is our last orbital, our 3p orbital, because we have to place 5 electrons. So we place them singly at first and then start doubling them up. So the reason that I write this out, because this is a lot of work, writing out all of these different arrows and all of these different subscripts and numbers. So the full electron configuration, this is what that is. All of the different numbers starting at hydrogen going to your desired element. But there's another way that we can write out electron configurations, and that's our condensed electron configuration. So we can shortcut. So if we basically look at this, our 1s orbital is completely filled. Our n equals 1 is completely filled. Then our n equals 2, which includes our s and p subshells, are completely filled as well. So what we call this is the inner electrons. And so these inner electrons lie very close. Oh yeah, I already have that. Inner electrons lie close to the nucleus, and we call these core electrons. And if we actually look at that, those core electrons take us all the way to neon, because there's 10 electrons there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So those core electrons take us to neon. So we can write a condensed electron configuration, and we can just condense all of these core electrons and just start with neon. So neon, and then we write out all of the electrons that can take us from neon to chlorine. So that's this last 7 electrons. So it's a shortcut. So this is called the condensed electron configuration or noble gas configuration. Oftentimes we will use this type of configuration, and it's fine to use because all that's left are n equals 3 electrons, and these are what we call our valence electrons, the outermost electrons. And it's those outermost electrons that are involved in chemical reactions. So all of these inner electrons typically are not involved in chemical reactions, so we can kind of just ignore them and just bunch them all together within this noble gas shorthand. So this is another way that we can write out an electron configuration using the condensed version. So oftentimes what I'll do is if I'm given an element, let's go for something crazy like antimony. We look at antimony, right? If I wanted to write out the full electron configuration for that, I would have to write out 51 different electrons, but I can shortcut. So usually how I do that is look at the element I want and just kind of work backwards. So go back in elements until you hit a noble gas. So the closest noble gas to antimony moving backwards, we must move backwards, is krypton. So for antimony, we could start at krypton and then just work our way up through elements 37, or no, not 37. So krypton will bring us to 36 electrons. So that gave us a 36 electron shortcut. We only have to go through 37 through 51. So from rubidium all the way to antimony. So the shortcut way is nice, and it can save you time. So another thing the noble gas configuration does is highlights these outer valence electrons that we've talked about. So it's showing you the most important part of the electronic structure, just the outermost atoms. So these are what we call our valence electrons, or those outermost atoms. We've already kind of touched on valence electrons when trying to determine charge of monatomic ions. So the number of valence electrons, or outermost electrons, so these are all the electrons that reside in the highest n value. So in this case, if we look at chlorine, these are all the electrons that reside within our n equals 3. And so there's a total of 7. So there's 7 valence electrons in chlorine. All right, so the number of valence electrons within a neutral atom is equal to its group number. So we already talked about chlorine. It has 7 valence electrons. It's in group 7a. So if we look at sodium, sodium is in group 1a, so it's going to have 1 valence electron. But if you also wrote out its full electron configuration or its noble gas configuration, you would see that that outermost electron it's a 3s1 electron, so it has 1 valence electron. So if we look at tin and where it's placed on the periodic table, it's in group 4A. So if we look at the outermost electrons here, that's n equals 5. That's the highest shell value. So you see that there are 2 electrons in each the 5s2 and 5p2. So that's a total of 4 valence electrons to match its group in 4A. So another way we can look at valence electrons for tin in particular, or any of these heavy elements, is really the valence electrons are really defined as electrons in the highest n value and in any partially filled subshell of a lower n value. So it also would be accurate to say that tin here has 14 valence electrons. And also on some periodic tables, you'll see that tin is also in group 14. So this would also work as well. So we would count these 4d10 electrons. But typically, to get you most of the way there, if we just look at the outermost electrons and the highest n value, that will also get you the number of valence electrons typically involved in chemical reactions.